So these were the outputs of the Excel multiple regression. And if you have seen some of the practice exam problems, what I do is I would like hide some of these values and you have to figure out what goes in there. So I want to explain to you what these numbers are and what kind of questions might pop up, okay? So first of all, you could be given multiple r, but not r squared, and simply the relation will be just squaring this will give you this one. So if you just punch these numbers in, and you take the square of that number, you're going to get the next number. Now, I briefly talked about adjusted R, but I didn't give you the formula. So let me provide you the formula. So you have adjusted R squared is given by 1 minus n minus 1 over n minus k minus 1, 1 minus r squared. So that's the formula. And the way you should read this is that, see, okay, so what's the meaning of r squared? Do you remember? This is called coefficient of determination. Do you remember the meaning of this?
How much of the data is correct?
So how much of the variance of the y, actual predicted variable y, is predicted or explained by the multiple regression. So I talked about this relationship that sum of squares of y is same as the sum of squares of y hat, okay, plus the sum of squares of the error. And there's a other name for this one. This one is the called the sum of squares of the regression. That's another name for this one. And this one is the sum of squares of the error. That's how people write it. But really, when you model y as, say, beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus some error. So maybe I should use epsilon here. That's the way we model the linear regression. Multiple linear regression assumes that the final output of y is like some linear function of 3 variables, x1, x2, x3 being length, height, and width, plus some constant, plus some error, which is due to something that you can't control. It's more like a random variable here. And we're assuming that this error has the average of 0. And if you assume that, then the sum of squares of this part plus sum of squares of this part would equal to the sum of squares of this part. So that was something that I proved last time. And the proportion of how much SSR takes in the sum of squares of y is what we call the r squared. That's the meaning of r squared, okay? So it tells you how much of the variance of the y is due to can be explained by the variance of y hat. So if you know that, what's the meaning of 1 minus r squared? That's how much it's not explained by the multiple regression. That's what it means, right? So you make that, and what you do is you can see that. Okay, let's look at this one. Is this bigger than 1 or less than 1?
Less than 1.
No, the denominator is less because you're subtracting k. What's k? K is the number of predictor variables. What's k in our situation? How many predictor variables do we have?
4.
The intercept is not part of it.
Oh,
It's
3.
These 3, okay? Intercept doesn't, see, beta 0 doesn't have a variable associated to it. The only variables that we have is x1, x2, x3, which are length, height, and width. Okay, so our value for k is 3. Okay, and therefore the denominator is a smaller value than the top value, which means this is a bigger value. Okay, so what you're doing is you're taking the unexplained part, okay, and by multiplying something that's bigger than 1, you're making this bigger, and then you're subtracting from 1, so that the adjusted r squared will be always less or more?
Less.
Less than the r squared. So you can see that adjusted r squared is less than this one. And what happens is that the bigger your predictor variables are, then the smaller the adjusted r will get. So in other words, it's kind of penalizing for the fact that you're just adding more variables to explain what's going on. Okay. And but of course, when you have a lot of observations, so right now number of observations is 35. If you recall the Excel file, we had 35 observations of the bream fish, and we're trying to predict the weight using the length, height, and width. So we have 3 predictor variables. So since n is 35, it's not that, it's like what, k is 3, so it's only 10 times bigger. So you get a small decrease, but if number of observations is something like 1,000, then this wouldn't change much, so that these two values wouldn't be that much different. Okay, so that's what it is, and the standard error is the sum of squares of the error divided by the number of observations. Okay, so that's what standard error is. And I can't recall if it's supposed to be divided by n, or it's either n or n minus k minus 1. I can't recall. But that's not important. This will always be given if you need it. So that's not it. Okay. All right. So that I've finished explaining this part. Now let's move on to the ANOVA part. So you're going to see this word ANOVA a lot. This simply is an acronym of analysis of variations. Okay, so ANOVA means analysis of variations. And you can see that the degrees of freedom here is, where does this 3 come from? Can you
The
guess?
amount of variables.
Number of predictor variables, 3. Where does the residual come from?
The remaining number for observations, but like -1.
Okay, yeah, that's right. So residual degrees of freedom. So let me also say residual degrees of freedom of the residual is equal to n minus k minus 1. Okay? So that if you add them, because this is k and this is n minus k minus 1, if you add them, you're going to get n minus 1. And then the sum of squares are these sum of squares that we talked about. Okay? So sum of squares of the regression, which is sum of squares of this quantity, the predicted values sum of squares. And always when we say sum of squares, you're always subtracting the average and then squaring them and adding them, okay? Without dividing by n. That's kind of easier because there's always this confusion of like, do you do Bessel correction or not? Like, but if you just say sum of squares, that doesn't come into play, so you don't have to worry about it. Okay, so that's what this first part is, and then this error part, the difference between y and y hat, and you take the square of it and you add them up, that's sum of squares of the error, and then the total will be this sum of squares of y, so the total will have this meaning. But usually what's going to happen is that this column right here and this column, these two values, those are only obtained after the Excel spreadsheet computes things, right? Does the linear regression. So those will, if you need them, you will never be hidden these values, because that means you have to do the entire multiple regression, which can't be done in a regular calculator. So those will be given. What could be hidden a lot of times is that you might be not given these, you have to figure them out. And then you may have to find all these subsequent numbers. So let me explain how you find these numbers, this number, and this number. Okay, first of all, this MS means mean squared, sum of mean squares, mean sum of squares, that's what it means. And what it means is you divide the sum of squares by the degrees of freedom. Okay, that's what you do. Okay, so if you took your calculator and you did this value divided by this value, you'll get exactly this value. You can try it to verify that it's true. And it's good to try it so that you remember, okay? So please take your calculator out and do this divided by this, and make sure it's this one. And then this f is simply this divided by this. Okay, that's what this f is. Now, why is it called f? I think f, people called it f because of, in the honor of this famous statistician named Fisher. He did a lot of analysis of variance. And so I need to explain quickly what F distribution means. So F distribution is so you remember the chi-squared distribution? Chi-squared distribution of some degrees of freedom, k. Right? What is that? That's if you have sum of some xi squared, where each of these xi's follow the normal distribution with 0, 1. So if this happens, then the squared quantity is a variance of a single value you get from here. So, and you're saying that actually, let me write capital here, because I want these to be random variables. The difference between capital and the small is that these are random variables which you don't know what the values will be, whereas small values are, small x means it's a realized value. So if you actually pick a number for this value, then you write small value. But anyways, so that's the meaning of chi-squared. So what it means is that if you have a case where you have a bunch of sum of squares, then this is the quantity that you use to figure out the significance of your test statistic. That's why we were using it for chi-squared goodness of fit and also chi-squared test of independence, right? So in the chi-squared test of independence, what did we do? We did expected minus, observed minus expected squared, and you divide it by expected, just like that, right? So doing this, well, it takes a while to prove that, but you can prove that if you do this, then this is going to follow the chi-squared distribution with certain degrees of freedom k. So that's what chi-squared was used for. But then, what F statistics does is, it's like taking two chi-squared distribution. So let's say P and then Q. And then you're dividing it by the degrees of freedom individually. So if you take some quantity that that's like the sum of squares, and you divide by the degrees of freedom, and then you take the ratio. This also follows another kind of distribution called F distribution, and it looks kind of like the chi-square distribution, except that I would say it peaks a little bit more. So that's what the F distribution has. And the usage of an F distribution is whenever you're trying to compare two quantities that are sum of squares. Okay? So that's why you're taking these sum of squares and you're dividing by degrees of freedom and then taking the ratio to get this value. And we know that this quantity is obtained in this format. We know that it should follow the F distribution. And then we look at this value and see what the area right of that value is. And that value is the significance of this F quantity. Now 167 is a really high value, so you'll see that this is 3.01 times 10 to the negative 19. So that means if there was no relationship between the weight and these three things, just having these high amount of explainability, see, this being a lot among this means that it's a high amount of explainability, right? Having that much explainability is very unlikely. So let's let me try to explain again what this value is. This value is like a hypothesis test. So in the hypothesis test, what do? We have the H0 and H1, right? And H0 is like saying, oh, the weight, it has nothing to do with these things. It's just like some average quantity y hat, a y bar, plus some error. That's all it is. Okay? That's your null hypothesis. And then your alternative hypothesis is, no, it's not. It's like some y. It's not y bar plus e. It's y hat plus e, where y hat is a linear function that depends on the three variables. That's what it means. Okay? So, and the way you're thinking of it is like this. Suppose this is what it is. Okay? Every hypothesis testing starts by assuming that the null is true, and you do the analysis, right? And then you do the analysis and you look at what proportion of the variance in y is explained by your regression. Now, let's think about this. If this has a very poor predictability of y, then the amount of the sum of squares of y hat will be very small compared to y, right? Is that right? Then that means this value will be small, which means this value will be large, because they have to add up to this one, right? So since this one's fixed, if this value is small, this is going to be large, which means that after you divide by the degrees of freedom and you take the ratio, this F statistic will be a low value. It will be some small value. If it's a small value, then the F statistic will be somewhere here, which means the p-value will be very large, which means that it doesn't have much significance. When you have a very small p-value, that's of high significance, okay? So you can kind of see why this kind of math would make sense, because we're doing something like an F distribution and then looking at the p-value from the F distribution. So that's what it is. Is that okay? Right. So on the exam, you might have just these given and this one given and these empty, and all of that, and you have to punch things in. Oh, I should explain this part. How do you get from here to there? Well, you would do FCDF in your calculator, and you do 167.8335, okay? And then until some high number, 10,000 or something. Put something big, million, something like that. Because you don't have a symbol for infinity, you just put some large number. And then to get this number, you need the numerator degrees of freedom, which is, what's our numerator? This is the numerator, right? What's the degrees of freedom to get this one? This is 3, right? So this is the numerator degrees of freedom. Whereas this one down here, this is denominator degrees of freedom. So you have to put in 3 and 31, and you put this into your calculator and press enter, you're going to get this number. Can somebody verify this for me quickly? You got it?
Yeah.
Okay. Yeah. And with, in your calculator, whenever you see E negative 19, that means 10 to the negative 19th power. You should know that, okay? Yeah. You have any question? Yes?
Where did the second number come from in the CDF after the 160?
This number, you're supposed to have infinity because what you're trying to do is, here's the F distribution, here's 167, and then you have to find this integration, so it has to be infinity. Well, you don't have infinity on a calculator, so you put something like a million.
Okay.
Yeah. And then 3 and 31, and this is numerator degrees of freedom, denominator degrees of freedom. Okay. Okay. Now we have to work on this part of the output. Again, this part, coefficient part, it has to be calculated using the Excel table. And I want to still give you some formulas that, although you're never going to use it, I still want to give you some formulas that would calculate this a little later. But for now, let's just accept that's true. Standard error also, there's a formula for it, but let's just assume that it's given, okay? The formula is just too involved to actually use it, so yeah. I'll describe the formula, but I wouldn't be able to really write in the format that you can use. So these two, we're going to assume that's given, okay? All right, so then everything else you should be able to fill in, and the way you fill it in is first the t-stat. So what is the t-stat? Well, as we know, the null hypothesis is that you have just null hypothesis is that y, the actual value is just some y bar plus some error part. Okay. In other words, we are assuming that you have some y bar plus 0 times x1 plus 0 times x2 plus 0 times x3 plus some error, right? So that, in other words, your null hypothesis is saying that the coefficients are 0. In other words, there is no correlation between x1, x2, x3, and then y. These don't have any predictive power in giving you the y. That's our assumption, all right? Since that's our assumption, that's your null hypothesis, you calculate the t-statistics just like how you would do it. How do you do that? Well, t, or t or z, the test statistics usually is your observed minus what's assumed, right? And you divide it by the standard deviation. That's how you do that, right? So, for example, the formula for z-score is x bar minus mu over sigma over square root of n, right? Something like that. If it's a, yeah. I have square root of n here, but this is the standard deviation of the average, and this is the observed average. This is the assumed population average. So that's your formula. So it takes the same format. So in our case, for example, if I have length, the calculated coefficient for the length is 12.0324. And then the claimed value of this in the null hypothesis is what? What's the claimed value of the coefficient of the length in the null hypothesis? The null hypothesis claims that there is no correlation, so it must be 0. Very good. Okay? And then you divide it by the standard error which is 7.615446. Okay? So in other words, it's simply this. If you divide this by this, you get the next number. You can check. Okay? Take this number and divide by this, you get this number. Okay, so you just divide, and that's how this t-stat is calculated. Now, something that's slightly not logical is that with this explanation, you should really be doing coefficient minus the y average, and then you divide by this. But I think even this row, you still just divide. Can somebody check? I think this divide by this is also this. Is that right? Or do I subtract y bar?
No, you just divide.
Yeah, you just divide. Okay, so yeah, so I'm not so sure. Does that make sense? I guess that's also the null hypothesis. So anytime you're trying to see the significance of these coefficients, what you're doing is you're testing against the null hypothesis, which is saying that those values are 0. Okay, that's the logic. Okay, so is this negative 1046.6 significant? Well, how do you say it's significant? You want to compare it to, say, if it's 0. Okay, so you subtract 0 from here and then divide by this number, and you get this value. So you get these t-statistics, and then you have to convert these t-statistics into p-values. And the way you do the p-values is the following. You do the inverse t. So, well, let me draw the graph too. So what you do is you're going to go to the t curve, t distribution, with the degrees of freedom, which is a residual one. So it's the 31. So we use 31. Don't ask me why. I forgot the reason. Why should it be this one? I mean, in general, when you talk about the degrees of freedom of the regression, this is what we talk about. See, when you have a simple linear regression where it's like y equals to b0 plus b1x, if you have this, then we just say degrees of freedom is n minus 2, which is really n minus 1 minus 1. You have one predictor variables and you subtract one. So when you have degrees of freedom of a multiple regression, you always talk about this one. That's what you do. Okay? So you go to the t curve with degrees of freedom 31, and what you do is you go to negative 11.585 and put also the positive one. And you're trying to test against the other claim where the alternative hypothesis is that this intercept B0 is, so what I'm trying to say is that null hypothesis will be saying that B0 is 0, then the alternative hypothesis saying B0 is not 0. Okay? So you do a two-tailed test. In other words, you can do inverse T of 11.585. So you just delete the minus. Again, some really high value, 10,000 or million or something. And degrees of freedom is 31. But because it's a two-tailed test, you multiply this by 2, and you're going to get this p-value. Okay. Same thing with this one. You just do, for this one, you do inverse t of 1.580044 to 10,000 and 31, and times 2, you get this value. Okay? So that's how you get the p-value. And the p-values kind of tell you the significance of these numbers. And what it means is the following. First of all, there's no way your coefficient could be this high just by chance. That's like 10 to the negative 13th power. That's like almost no way. And even this one, there's no way that your height would have this such a big coefficient. Okay? So that's what this is. However, there's like a 12% chance that you would have gotten a length coefficient something like 12, just by chance. Okay? The same thing here. There's a 20% chance that you would get a number like 45 just by chance. Yes?
Did you mean TCDF?
Oh, sorry, it's not inverse T. Sorry, it's TCDF. Yeah, thank you. Should be TCDF 11. Yeah, thank you. Okay. So, okay. So please verify this, and then what this tells us is that maybe the length and width are not so trustworthy. Okay, that's a very important finding. This report, you might see, okay, well, what's the point of all these other numbers? Don't we just need the equation? Because, see, what is the actual equation we get at the end of the day? It says that our predicted y is negative 1046.6 plus 12.0324 times x1 plus 62.819859 x2 plus 45.89766 x3. That's really the most important result of this multiple regression, right? But this would only make sense if you can trust these coefficients. And it turns out that these coefficients are not so trustworthy, whereas these are very trustworthy. And you can even see this in the confidence interval. So here we have a 95 confidence interval. And as you can see, the confidence interval for the intercept doesn't contain 0. 0 is not in here, right? But look, the 95 confidence interval for the length does contain 0. This is negative, that's positive, so 0 is somewhere between. Which means there is more than 5% chance that the original coefficient for the length was 0, and you just had a bad sample that just somehow gave you a very high value. Right? So this coefficient is not so trustworthy. Okay. So if the question was, what are the most significant coefficients? Well, you don't say intercept is a coefficient. In that case, among length, height, and width, we should say that height is the only thing that we can really trust. The other ones are not so significant, because those are above the significance threshold. Okay? All right. Okay, so finally, now let's think about how to get the confidence interval. To get the confidence interval, it has a similar formula of the confidence interval that we've been using before. So small b1 is the coefficient obtained from sample. Okay. Whereas beta 1 is the questionable actual coefficient that you would have gotten if you were able to capture all the bream fish on the earth, and you measure them, you weigh them, and that value would be beta 1, which we don't have access to. Okay, so coefficient from population. Now there's no way we can catch all the green fish, so beta 1 is something that we don't have access to. But we can still talk about the confidence interval for beta 1. And the way we do it is we say beta 1 is between B1 plus margin of error and B1 minus margin of error. Right? That format is same as before. What's slightly not true is, say, for these we're saying that those follow T distribution, normal distribution. All of these are symmetric distributions, so they always follow some value plus margin of error and some value minus the margin of error. But if you have something like an F distribution or chi-square distribution, then those are crooked. So even if you have a value, the confidence interval is not symmetric with respect to that value. So that's, yeah, I haven't talked about that, but maybe if I have time, I might talk about that. Yeah, but anyways, that's the format, and the margin of error is similar to our previous formulas, which is like T alpha over 2 times the S of B1, where standard error of B1 is this one. And then this again is B1 minus T alpha over 2 times S B2. Okay? No, B1, sorry. Same. So same margin of error, plus and minus. Now, what is T alpha over 2? This one is the inverse T of 1 minus alpha divided by 2. So we're doing 95% confidence interval, so significance level is 0.05. So you do 1 minus 0.05 divided by 2, which, and then again, let's see. Yeah, so you do that, and then you put degrees of freedom, which is 31. Can somebody calculate this for me? What do you get? 2 point something.
Negative 1.695.
No, that's not right. This is 1 minus 0.05
Oh,
over 2.
2.0395.
2.03 what?
95.
95. Okay. Okay. So that's what T alpha over 2 is. So what you do is this is your B. This is your B1. This is your SB1. Okay. So you have B1 plus 2 point. So this will be B1 is 12.0324 plus 2.0395 times SB1 is 7.615446. And if you do that, you should be getting the upper bound, which is this. Okay? And then instead, if you put this into minus, you're going to get the lower bound for the confidence interval. So you do that for every part, that's how you get these values. Okay? So by being able to fill in the missing information, you can have a better understanding of how this report is generated, and from there you can have a better judgment of how useful your multiple regression is. Okay?